Right, good afternoon, everyone. Hope you had a good lunch. Welcome again to the DataStax Day Munich. Thank you for coming back from lunch. Always good to see people coming back for the afternoon session. But given that it's the first session after lunch, if people fall asleep, I really won't be offended. In fact, it's probably quite normal. So I'm going to give an introduction this afternoon to the use of Cassandra and Spark with DataStax Enterprise. We've heard a lot this morning about DataStax Enterprise itself and Cassandra and the benefits of Cassandra and Spark. So we're just going to dig a little deeper into how Cassandra and Spark work together and why you'd want to use them together and what benefits they bring. Just a quick word about me. Like Tim, you've heard this morning, and like Najib, you heard this morning, I'm also a long history in Oracle. Again, mostly around databases. Started out as a database administrator on version 5 of Oracle, so that's some time ago, as you can guess. But latterly, solutions architect around EPM and an e-business suite, Exadata, OBIE, that kind of technology. But having made the jump to NoSQL, I'm really pleased to be here. It's a really exciting world to be involved in. There's a lot of really interesting technologies, and you can make them work together in really, really exciting ways. And you can build the sort of solutions that you really can't build with these traditional technologies. And if you do try to build them with these traditional technologies, they tend to be very expensive. And as you saw this morning from some of those other reference architectures, they tend to be quite complicated solutions. The benefit of Cassandra and Spark working together, they work, especially in the DSE integrated platform, they work together really quite seamlessly and straightforward to integrate. So just a quick recap on Cassandra. I know we talked about it this morning, but just for those who missed out on some of the basic details, it was originally started at Facebook in 2008. They wanted to build a messaging platform. There were 2 white papers that had come out around that time, the Google Big Table white paper and the Amazon Dynamo white paper. Both of these described in various ways how you would architect a distributed database at scale. Facebook took these 2, put them together, came up with their messaging platform, and then they ultimately open sourced it, and it's been an Apache open source project since 2010. And that's about the time that DataStax formed to provide that enterprise support for those Cassandra customers. We know it's very, very fast, very, very performant, a high throughput, ideal for a fast transactional database. And it's extremely resilient. You can distribute your data across multiple data centers. It's designed for no single point of failure. You can lose a node, you can lose a data center, you can lose a rack, but that doesn't mean you lose access to your data. So for that reason, in the Cassandra world, we don't talk about high availability, we talk about continuous availability, and we don't talk about disaster recovery, it's disaster avoidance. You shouldn't need to lose access to your data in a correctly configured Cassandra cluster. You've also heard that it scales in a linear fashion horizontally, so it's very easy to upscale. If you want 25% more throughput, you add 25% more nodes. If you want 50% more storage, you add 50% more nodes. It's very easy to mathematically calculate how you'll scale up a Cassandra deployment. And it's very easy to operate. It's got a very low total cost of ownership compared with some traditional technologies. Netflix, when they migrated from open source to DataStax Enterprise at the time, they had 2,700 nodes, and they migrated that with 2 people. Now, if you speaking as an ex-Oracle DBA, if you try to upgrade 2,700 databases, that's pretty much a lifetime's work in front of you. So there's a major difference in the amount of effort involved. And of course, as we've said, the database, the enterprise version of the Cassandra platform is available from DataStax. So we've talked about Spark this morning. For those of you who are new to Spark, what is it? Fundamentally, it's a distributed in-memory computing engine. So in the same way that Cassandra is a distributed transactional processing database, it's a complementary technology because it's a distributed in-memory computing engine. So in the same way, if you want more capacity, you just add more nodes. You can scale up to cater with bigger workloads. Again, it's been an Apache project since 2010. It's very mature. There's a lot of uptake in the industry. It's very popular. And it supports both batch and streaming analytics. I mean, other streaming engines have come along since then, for example, Storm, but Storm doesn't do batch analytics. So the fact that it provides both batch and streaming, and it's very proven in the marketplace, mature, makes it a very popular choice. It's very fast, primarily because it runs in memory, but it's typically 10 to 100 times faster than a corresponding job running on HDFS Hadoop MapReduce. In terms of development, it's got a very rich Scala API and Python, Scala, Java, and Python APIs. So for developers, if you're used to using those kind of languages, it's a very comfortable environment to work in. And while Spark R is now available, you typically, if you're doing jobs in Scala, you'd be generating a lot less code than you'd be doing a corresponding job if you were coding it in R. So you can get up and running and start churning out code a lot quicker than you would do, for example. Why do we want Spark and Cassandra? Why have DataStax integrated these two together? What's the benefit? What does it bring to the party? Well, obviously, if you're ingesting a lot of data into Cassandra, you want to be able to provide some analytic capability on that data. Whilst Cassandra is scalable, fast, resilient, does all those fantastic things, it doesn't have any mathematical or arithmetic or aggregating capabilities. So if you want to do analytics on the data that's in Cassandra, you need some other tool to do it. And that's why DataStax took the decision to integrate with Apache Spark. What it does do is it allows you to perform all the kind of analytics that you would want on the data that you're holding in your Cassandra database. So not only can you lift data out of Cassandra and process it in memory on your distributed Spark framework, but you're lifting data out of a NoSQL database. There are things that you can do with Spark. Spark provides a very rich Spark SQL API, for example, that once you've lifted that data into tables, you can then start doing cross-table relational stuff that you could do within a relational database. So it does add another level of functionality to the data that's stored in your Cassandra database, whilst allowing you to perform all these other rich analytical processes on top of it. Another big use for Spark is integration and transformation. Spark's got connectors for pretty much everything. So if you want to take data from DB2 and push it into Cassandra, or take data from HDFS and put it into Oracle, Spark can pretty much take data from anywhere. So in fact, it's a great tool for doing data loading into Cassandra. It's a great tool for doing an initial migration from a relational database and pushing that data into Cassandra. And as you'll see with some of the reference diagrams a bit later on, it's a great tool for integrating your new NoSQL transactional platform, which you're building out, and allowing you to still retain the ability to integrate it with data that might be held in your historic or legacy or traditional databases, which is still part of your corporate computing landscape. We also use Spark extensively for streaming. We'll talk a little bit about that in a moment. So that allows us to take care of really fast ingestion. So these days, data's arriving very quickly. There's a lot more of it, whether that's cash registers or market tick data or vehicle telematics, whatever. You need to be able to cater for streaming that data in very fast, and Spark is a great choice for doing that, especially when you're working with Cassandra, given that DataStax have integrated the two so well for you. And we'll talk a little bit about that. So I said that Spark is fast. How fast is Spark? Well, there's the Dayton Gray sort contest, which tests how fast systems can sort 100 terabytes of data, which is a trillion records. Previously, that record was held by a MapReduce cluster, and they used 2,100 nodes, and they completed that in 72 minutes. You're probably reading ahead of me, so you'll have seen that in 2014, the benchmark was broken by Spark completing it in just 23 minutes on 206 nodes. So they did it 3 times quicker with 10 times fewer machines. They also sorted, there's not part of the Dayton Gray benchmark itself, but there's another test with a petabyte of record, which is 10 trillion records. And they did that on 190 machines in 4 hours, which was 4 times quicker with 20 times fewer machines than a corresponding MapReduce job. So whilst it's always the story. There are certain tools which are good for certain jobs. If you do really on a regular basis want to trawl through petabytes of data and speed isn't important, then there's still a place for things like MapReduce. If you want to be able to process data in memory and get those results back on a much quicker, then Spark is probably a much better choice for you, particularly if you're working with data that's already held in Cassandra. How does Spark connect to Cassandra? DataStax provides the Cassandra Spark driver. It's open source. You can download it. You can play with it. It's compatible with all recent versions of Spark, of Cassandra, DataStax, Scala, Java, Python, etc. And what it does, it exposes Cassandra tables and allows you to pull them into both RDDs and data frames. RDDs and data frames, if you like, the kind of the basic structures which you use to store data within Spark. One is a resilient distributed data set that was used a lot, very, very effectively, but in Spark 1.3, Databricks came out with, Databricks being the commercial sponsors behind Spark in the same way that DataStax are the commercial sponsors behind Cassandra. So Databricks came out with something called data frames, which are much of an improvement. They allow you to view the data that you've loaded in a columnar tabular format. So you're seeing the data as tables, and it provided a very rich API, querying API on the data that you've pulled into that data frame. So basically, you're lifting data out of Cassandra into these data frames and then being able to access data in these data frames as tables in memory. You can also, from Spark, you can execute, using the driver, you can execute SQL queries directly on the underlying Cassandra table. So you can just query the tables and pull stuff out, do stuff with it, and save it back. Very, very effective at doing that. And because you're using an in-memory distributed data set, so the data that's spread across your cluster of Spark machines, you can process very large volumes of data. If the volume of data that you want to process increases, you can flex up and add more nodes to your Spark cluster. So that's the benefit of using a flexible distributed technology like Spark. And it complements Cassandra very well for the same reasons. You can then, once you've processed that data, you can save that data back to Cassandra using the save to Cassandra call. And if you want JDBC or ODBC access, if you're using something like Tableau or any of those BI tools, whatever, and you want to be able to access data in Cassandra, Spark also provides a thrift server, which allows JDBC, ODBC connections to the data that's held in Spark, and the underlying Cassandra tables. So the way that we integrate Spark with Cassandra in the DataStax platform. So typically, if you were going to go with an open source Cassandra or a DSE Cassandra cluster and you were playing with open source, you would be moving data backwards and forwards between two clusters of machines, using the Spark driver probably to connect to the DataStax cluster. So you pull data out of the cluster, you'd move it across to your Spark cluster, you'd do something with it, and you'd save it back. Unfortunately, because you're moving data around, the best you can hope for there is millisecond transfer times. And in terms of data processing and being able to analyze data very quickly, you want to reduce that latency as much as possible. So for that reason, that the DataStax architecture is to co-locate the JVMs for Spark with the JVM for Cassandra on the same nodes. Those nodes are also data locality aware. So each of those nodes is aware of the range of tokens in the underlying Cassandra tables on that node. So when you say load the data into Spark, each of those Spark JVMs knows which data is in the underlying Cassandra node that it's sitting on. So it intelligently lifts only that data. So you haven't got Spark nodes going across the cluster to pull out of that node and out of that node. It's very intelligently lifted out of the Cassandra nodes into the corresponding Spark JVM. So it's a very, very efficient process. You're reducing the latency of the data transfer between Spark and Cassandra from milliseconds down to microseconds. So there's a massive improvement in performance in the way that the two are integrated. So looking at analytics then, we talked about batch and streaming. You know, there are different types of use cases. Batch analytics tend to be something that's regularly run, repeatedly run, large to massive data sets. Can be ad hoc, or it can be a routine batch every minute or every 5 minutes, roll-ups every hour, whatever, trawling through the data. Whether it's for analysis or research, whether it's retail or commercial, these are the sort of things that need to be routinely run on the data that you have in your database. So it tends to be slow or static data. Streaming data is a somewhat different use case. This is where you want to perform real-time analytics on data that's being streamed in. So these are typically industrialized or commercial processes, things like sensors, as we said before, tick data, transactional data. Maybe you want to intercept click streams from a website to provide real-time personalization on things as they're happening in real time. And in many cases, this is data, especially from a safety or a financial consideration, this is data that cannot be afforded to be missed. It has to be processed at that point in real time. So we'll look at those one at a time. Just a quick word on the architecture, again, of how Spark and Cassandra work together in a DataStax cluster. So there's a one-to-one correspondence between each of the Spark workers on each of the nodes with the Cassandra process. But within any Spark data center, there is one Spark master. Now, a Spark master is elected when you start up using a Paxos algorithm, and in the event that the Spark master fails, the Paxos algorithm will elect a new Spark master automatically. So when you, for example, when you create a Spark job, you have your code in your driver program. You create what is called a Spark context. This sort of defines some aliases and some connectivity to the Spark master and the Spark cluster. And then you kick off your job, and your job is submitted to the Spark master. The Spark master accepts that job request and then farms it out to the Spark workers on each of the Spark nodes. Those Spark workers will then create Spark executors or start Spark executor threads to actually perform the work. Those Spark executors are then capable of reading the data from that Cassandra node, doing some manipulation, some processing, some aggregation, whatever, and then persisting that data back into the underlying Cassandra node when the processing is finished, if that's what you want to do with the data, or it can be written to some external system for consumption into a dashboard or whatever, but you have the ability to read and write from the data in the Cassandra, the node that the Spark JVM is sitting on. So we talked about Spark streaming before, so we need to be able to capture, prepare, and process fast data. We need a different approach from traditional batch processing. It's got to be now. You want to be able to provide immediate insight. You want to be able to react to it in real time very quickly. So we talk about streams of data, but even streams of data can mean different things to different people. A stream of data, to me, suggests something quite gently moving, some placid, moving piece of, and it might be something that's quite manageable. So, for example, a retailer might be getting 1 million credit card transactions a day. Sounds like a lot, but it's still only 10 requests per second. So, in fact, that's quite a moderate data requirement to manage. Something like Spotify, that's like an order of magnitude or more up, or in fact, more than one order of magnitude, but it's a bigger use case. So we're talking about terabytes of data per day. So here we're talking about billion transactions. That's 10,000 transactions per second. So now we're starting to talk about heavy use cases. And then we look at something like Netflix. Now, Netflix ingests petabytes of data per day. They're talking about over 1 trillion transactions a day. So that's 10 million transactions a second plus with DataStax Enterprise. And of course, they're using 10,000 plus nodes distributed globally. So we are talking about a big cluster. But again, it serves to demonstrate that the DataStax platform can scale in a linear fashion regardless of the volumes and the scale of the data that you're working with to ingest. Just covering briefly then some of the different types of streaming use cases we could be talking about where data, it's important to deal with data in real time. So transactional data, missing this sort of data could have huge financial implications, things like credit card transactions, market tick data, etc. Credit card fraud, bank fraud is becoming an increasingly popular area of activity for our customers, especially when you consider that $16 billion was the value of the global credit card fraud industry last year. So there's a lot of money to be saved by financial organizations that can get a grip on this and start to deal with this in real time. And we're talking about use cases where credit card transactions are intercepted at the point of, or from the point of sale, and then the query is sent back to the point of sale in real time to ask for more ID, for example, before the transaction has actually taken place. Traditionally, you would have run a nightly analysis job to determine which credit card transactions were fraudulent. Now you're in a position where you can actually intercept those transactions before they happen in real time. Things like user experience, so if you're clicking through and we're intelligently looking at the click streams, determining what adverts to place in front of you, what content to place in front of you, based on a real-time analysis of what you've been doing in the previous 5 minutes, for example. Again, of enormous potential benefit to retailers. Social media, companies are interested in the sorts of trends that, what are people saying about my product on social media and being able to react to that. And lastly, of course, things like sensors, so telematics, power stations, wind turbines, smart meters, electricity meters, that kind of thing. Again, potential safety implications there if you miss an opportunity to deal with that data in real time, if there are certain events that have to be trapped. So what do we need for a real-time streaming analytics architecture? If we want to be able to stream and intercept and work with traffic in real time at scale, we want something that's able to process extremely quickly and process that data with low latency. And for that reason, the sort of distributed in-memory architecture I've described previously is an ideal solution to that kind of use case. And for these sort of things, we're increasingly looking at a technology stack which is comprising at least what we call the Holy Trinity, which is Kafka, Spark, and Cassandra, but they make up 3 of the 5 components that Najib described before, which is the SMAC stack, and the SMAC stack is becoming increasingly popular as a solution for these kind of real-time streaming use cases. The additional parts being akka for a microservices-based perhaps aggregation web layer on an underlying Mesos infrastructure framework. But the 3 essential components we'll look at in a moment will be Spark, Kafka, and Cassandra. All 3 of these follow the same kind of distributed paradigm. They're all scalable, they're all distributed, and they're all highly resilient. So we've talked about Cassandra, we've talked about Spark. So what's Kafka and where does that fit in? So for those of you that might be new to Kafka, again, it's an open source project. It's been open source since 2011, so the same sort of vintage and same sort of maturity as Kafka and as Spark and Cassandra. And it's used pretty much everywhere these days. It's not many high-profile companies that aren't doing something with Kafka. And in the same way that Databricks and DataStax are commercial sponsors behind their products, the company that provides the commercial support behind Kafka is a company called Confluent. What can Kafka do? We'll get into the weeds in a bit more detail, but at a high level, it's very, very fast. It can handle hundreds of megabytes of reads and writes a second from thousands of clients. So it's very, very scalable and very, very powerful. The messages are persisted on disk, and they're not automatic. Unlike some queuing technologies, when you read a message, it isn't automatically deleted. It's up to you how you manage the retention of those messages, which also provides a very good recovery mechanism because your consumer can then seek back to a point in that log to recover from a point where it might have failed, for example. Kafka uses brokers. We'll talk about brokers, but each one of those brokers can handle terabytes of message before you even start looking at any sort of performance impact. So it's very, very powerful, again, as I said, and scalable, and very, very resilient and fault tolerant. What Kafka does, it attempts to, or serves to separate from producers from consumers. So Spark would be the consumer pulling stuff out of the Kafka queue, and a process which is maybe aggregating data from a number of sensors will be a producer, and it's pushing data into the Kafka queue. So Kafka can contain multiple feeds of messages. It does that in something called a topic, and it does that using one or more servers, which is called a broker. So if we break down that architecture a little bit more, we talked about decoupling producers and consumers. To make that more obvious, a colleague of mine came up with this analogy, which I rather like. If you're in a restaurant, for example, and you have one diner and you have one chef, the chef is the consumer. He's receiving the orders from the customers. The customer is producing one order at a time. The chef knows where that order came from. He knows what he's got to do with. He knows the order they came in. That's very easy to deal with. As you increase the number of diners in his restaurant, he starts to get a bit confused because he doesn't know which message came from which customer, what order they came in, who he's supposed to be sending the orders back out to. So in this case, we introduce a broker, and a broker is a waiter. A waiter effectively ensures that the orders are taken taken in the right order and served by the chef in the right order. And as you upscale the number of consumers, or sorry, the number of producers of these orders, you might need to increase the number of brokers and chefs. And that approach is scalable. You just increase the number of waiters and the number of chefs as you increase the number of producers. So as the volume of your data increases, you can very easily increase the scalability of your Kafka broker and your Spark consumer. It's a very, very complementary set of technologies. So say, for example, we have a weather station. Now, a topic can have multiple partitions. So say, for example, temperature. There's a lot more temperature data coming in than there is rainfall data. So you might have a separate topic for rainfall and a separate topic for temperature, but you might have multiple partitions within a topic for temperature to enable you to scale up to have more consumers to consume that data. So this is how Kafka scales. You can have topics, and then you can have partitions within topics, and then if you need more brokers, you add additional machines with more of the same topics being handled by more and more Spark consumers. So this architecture allows you to scale up as your volume of data ingestion and your data throughput increases. What this does, this allows you then to start to build out this kind of reference architecture where and this is a typical SMAC stack, high-level view. So you've got your sources of data, your producers, if you like, over there, which could be cache tills, they could be sensors, whatever. You have some kind of signal aggregation service, which might be a microservices-based solution written in Akka, for example. But that's pushing data into your distributed message queue, which is Kafka, which can scale up as required. You're consuming that data through Spark consumers, again, which can be scaled up as required, and they're persisting data into your Cassandra database, and your Cassandra database can be scaled up as required, depending on your requirements and your volume of traffic. The beauty of this is that while that data is in memory in Spark streaming, you can then run all the in-flight, in-memory, real-time analytics on that data that you need to be able to take those insightful decisions, to be able to intercept potentially harmful alerts on sensors, to detect potential fraud cases, to react to changes in market tick data to buy or sell stocks. So this ability to intercept data while it's in traffic, while it's in flow, presents a lot of other functional possibilities in the way that you build your applications and respond to your customers. You might have heard workload separation mentioned in some of the early discussions. Primarily at the top left, you'll see that we have this multi-data center approach in Apache Cassandra in the underlying Cassandra database, which allows us to not just replicate data between data centers for resilience, but to distribute data geographically so that you can bring data closer to your users, so that you can reduce the latency, so that if you've got users in the US, they haven't got to go a big hop across the Atlantic to connect to London. They can connect to their data center in the US. And as people update data in their respective data centers, it's replicated seamlessly and transparently backwards and forwards. What that does is it allows us to build out a workload separation architecture where you dedicate different data centers to different parts of the processing. So you have one data center which is dedicated just to OLTP with Cassandra, and you have another data center which is dedicated purely to analytics. This allows you to separate your analytic workload from your OLTP workload so that the number crunching at analytics isn't going to impact the experience of your end users connecting to your OLTP database. It also means that you can dedicate bigger, crunchier, heavier duty machines in your analytics data center for the heavier workload that they're going to perform. So this workload separation, again, is a very powerful feature in the way that we've implemented analytics and search in DataStax Enterprise. Looking again at some more reference architectures, this is an energy customer of ours who's implemented smart metering. So they have smart meters that feed into a Kafka queue, that go to streaming, that go to an analytics data center. As it's in flight, and once it's in that analytics data set, that particular customer can analyze that data, produce dashboards, monitor it, look for exceptions, look for people who are perhaps stealing energy because their consumption's abnormal, all the things that you would expect to be able to do with analyzing that data while it's in flight. But they can also replicate that data transparently, immediately to a customer-facing data center so that customers can log into that data center and they can see their energy utilization in real time. They can see trends of analysis, whether their usage is increasing or decreasing, whatever, over periods of time. They can view historical data. So it presents another, a lot of interesting opportunities in the way that you are able to interact with your customer once you've implemented this kind of infrastructure, physical deployment. And again, as I mentioned earlier, if you're implementing something like DataStax Enterprise as a part of a tech roadmap to building out a new performant, transactional, multi-data center, globally resilient database, you still retain the ability to interact with the data that's in your traditional database using the Spark layer as a transformational integration layer, which allows Cassandra to talk to all those other sources of data, whether it's DB2 or Oracle or SQL Server or Parquet files or MongoDB, whatever. The rich abilities of Spark in this area are very, very powerful. You also still retain the ability to stream data in from fast data sources. And this, if you're interested in the idea of a Lambda architecture where you build out a fast and a slow layer, this can be a very, very valid approach in helping you to achieve that. You can have a data source which splits into your existing traditional databases whilst at the same time being fed into your speed layer where you can perform analytics using Spark once it's in the Cassandra database. So that's the end of my discussion.